Hello, welcome to ePort 13. So this is the first video of two, and in this first video I'm going to be showing the ALU circuit, which is pretty much the main part of the microprocessor that we have been building up to all semester. Here I have the original ALU circuit we were given for the microprocessor. Our task was to add 4 extra functions to what is already here. So I went ahead and created a new subcircuit, copy and pasted this ALU circuit into it, and just added 4 new functions. So here is the ALU circuit that I have created. So I have some notes off to the side, and here are the modes I have. So the first 1, 2, 3, 4 up here were what was given to us. We have the option of either subtracting A or B, adding A and B, multiplying the least significant bits, multiplying the most significant. The 4 I have added are the ability to not the A input, or A and B, or A or B together, negate the B input. Let me go ahead and add that real quick, just to make it a bit more simple to understand later on. I also have the ability to shift the A inputs left by a certain number of bits. So let me go ahead and just walk you through what I have created. So to kind of make it a bit more clean, a bit more simple, I have created this subcircuit, and here are the 4 new functions that I have created. So let me go ahead and open it. I called it ops just for operations. But anyways, here are the four new functions I've created. So as you can see, it's already nodding the A input. A input is all at 0, so it's gonna show the inverse, of course. It's gonna invert the bits. Let me go ahead and just do 2, and there we go. I'm going to demonstrate next it ORing A or B together. So to do that, I'm going to go ahead and OR A or B together. So A is going to be an input of 2. B, I'm going to go ahead and do 4. And ORing these 2 inputs together gets you an output of 6. Awesome. And from here, I'm going to just negate the B input. So to negate the B input, you need to trigger S1, keep S0 off, and I'm going to just do 2. I'm going to go ahead and work off to the side real quick just to confirm. So first, to negate this, it's going to do the 1's complement of the input. So the 1's complement of B is going to be 1101, add a 1 bit to that, and then you get 1110. It works. Okay, and from here I'm going to go ahead and shift the A inputs to the left. So I'm going to go ahead and trigger both of these S switches, and I'm going to do an A input of 2, and let me go ahead and just, so we use this little pin I have right here that is connected to the shifter to go ahead and shift the bits by however many. So I'm going to go ahead and just shift it to the left by 1 bit. Let me do 2, and if I do 3, it's just going to push it all the way out. Those are the new functions I have added to the ALU. So to work it out, so this entire ALU circuit, of course, works with what's in here and this new in my ops subcircuit and without. So to use what's inside the ops circuit, you need to trigger S2, and then you can use the S0 and S1 inputs. But to use, just do standard, the standard arithmetic options that we were originally given. Keep S2 off, and then continue working through it as you usually would. So following this table here, I'm just going to go ahead and just start demonstrating how the ALU circuit works with and without the S2 switch being triggered. I'm going to go ahead and just subtract A and B. So I'm just going to go and do something simple. I'm going to do 3 minus 1. You get 2. How about 4 minus 2? You get 2. So it works there. If both S switches are off, you have the ability to subtract A and B. And the next one here in the table, you have the option to add A and B. So I'm going to go ahead and trigger S1, keep S0 on, and keep S1 off. And I'm going to go ahead and just do 4 plus 2, you get 6. 2 plus 2, you get 4. To multiply the least significant bits, trigger S1, keep S0 off, and then I'm going to do multiplication. 2 times 2, you get 4. 2 times 1, you get 2. Of course, duh. If you try going and doing multiplication on this with the most significant, I guess, bits on the left here, it's not going to work. To do multiplication with those, you have to trigger both S switches, being S0 and S1. So I'll go ahead and I'll do 3 times 3. You get an output of 9. So that is the new ALU circuit, which I will be implementing to the microprocessor. But to answer the question, which is, so it's useful to have a multifunctional calculator at the center of a microprocessor because first of all, having an ALU at the center of this microprocessor is useful. It allows this microprocessor to just perform a multitude of tasks, such as these mathematical operations I just showed. Having this calculator, the microprocessor will execute whatever instructions you input. It performs the calculations as quickly as it can because, after all, the ALU, this is a combinational circuit, so everything is immediate like that, unlike a sequential circuit. All of this is essential for modern computing. All of this is at the center of the computer you're most likely watching this on now. So, going to my microprocessor, it's been in use, as you can tell, but over here I do have my ALU subbed in rather than the old ALU we have here. And in the next video, I will go ahead and I will demonstrate its use.